Thank you. So now you can see my screen, right?
Yes.
Yes. Thank you very much. Thank you very much for your invitation. And today I will discuss Lagrangian formalism in terms of intrinsic geometry of PDEs, as it was said previously. So first of all, I'd like to formulate two main problems of this topic. How is the Lagrangian formalism encoded in the intrinsic geometry of a differential equation? This question is a bit strange, maybe, but still, it's one of the main questions of this discussion. And the second one is, does the concept of presymplectic structures describe the Lagrangian formalism completely at the intrinsic geometry level? Later, I will explain.
I'm sorry, you will explain what you mean by a presymplectic structure, yes? Or
yes,
yeah, okay.
I will explain it later. Yes, of course. Okay, and as main results, I can say that first of all, I'm going to introduce the notion of internal Lagrangians as an answer to the first question, and also I will introduce spectral sequence for Lagrangian formalism as an attempt to answer the second question. However, to be honest, I have no rigorous proof of any ideas about the second question, just a spectral sequence and explanation of places where the concept of presymplectic structure can be incomplete, where we may be need for something more, something else at least. So first of all, I'd like to introduce basic notations. Let us consider a smooth vector bundle pi. Here we have n-dimensional smooth base M and n plus m dimensional total space E. x1, etc., xn are local coordinates on M. They will play a role of independent variables. And u1, etc., um are local coordinates along the fibers of pi. They will play a role of dependent variables. The bundle pi determines the corresponding bundle of infinite jets with adapted local coordinates u, I alpha, and operators of total derivatives, dxk. These operators of total derivatives span the Cartan distribution. So here just alpha is a multi-index of the form of ordered set of integers, non-negative integers alpha 1, alpha n. And the absolute value of alpha is just sum of its coordinates. Okay. By Cartan forms, we shall mean differential forms vanishing on the Cartan distribution. A Cartan 1 form can be written as a finite sum of the form which is represented here. So theta, I, alpha are just contact forms, and any Cartan 1 form is a linear combination of contact forms with some smooth coefficients. These smooth coefficients depend on a finite number of coordinates on the infinite jets. Cartan forms allow one to introduce horizontal forms on infinite jets as an element of the factor model, which is represented here. Each horizontal K form has a unique representative of the form 1. I will call them horizontal representatives. So each horizontal K form can be identified with the form represented, which is written in the formula 1. And here components of this form are also smooth functions of a finite number of independent variables, dependent variables, and their derivatives. And this number is not restricted, just it should be finite. So let's denote by kappa the model of characteristics of symmetries, and a characteristic phi determines the corresponding symmetry of jets in evolutionary form, which is written here. I will denote them E phi. Let L be a horizontal n form, which is written in the horizontal representative form, represented in the horizontal form. Then the corresponding variational derivative can be written as follows. It's written in formula 2. is just usual Euler operator or variational derivative, but it's written in the form of a differential n+1 form. So the Euler operator arises in the Vinogradov spectral sequence for jets, namely the round differential D, which is just a exterior derivative. So the round differential D induces the Euler operator by the formula 3. Here, C2 lambda denotes the wedge square of the ideal of Cartan's form, I will call them twice Cartan forms. C2 lambda are twice Cartan forms. They are at least twice vertical forms. So each form from this model contain at least two multipliers of this form theta I alpha. Maybe 3, maybe 4, but at least 2. Each form that belongs to this model. The relation between the operators T and E, between the exterior derivative and the variational derivative, can be obtained from the Noether formula. More precisely, there exists a Cartan form omega L, Cartan N form, such that Lie derivative of L can be written as it represented under the formula 4. Here we have horizontal differential that just acts on horizontal forms, or on horizontal representative if you want. And also I use the notation of brackets with H, with subscript H, is just choice of the horizontal representative. As we can remember, horizontal forms are equivalence classes, so we can choose horizontal representative. These brackets denote, these brackets just mean choose of the horizontal representative. Then formula 3 allows one to conclude that the formula 5 holds. In fact, for some form omega L, this form omega L is just can be, this form omega L just can be obtained from the Noether formula. So it's written here, actually. Any form omega L that makes this formula, that makes this formula to be true, that makes this formula right, can be chosen as omega L in the formula 5. For example, if I have a Lagrangian L for in the following form, in the represented form, then I can evaluate its Lie derivative using integration by parts. So here we have total derivatives of phi, and just integration, usual integration by parts, allows us to obtain the corresponding omega L. So the choice of omega L, the omega L can be chosen in non-unique way, but still at least one of them, this formula gives us one of them, at least one of omega L. So in what follows, we always assume that a system of differential equations f equal to 0 is given, and we denote by epsilon its infinite prolongation. Its infinite prolongation consists of all its differential consequences, and its infinite prolongation is just submanifold of the infinite jets. Here we do not require that the number of equations equal to the number of dependent variables. So number of equations can be any number of equations. We consider situations with any numbers of equations, an m-dimensional bundle. So we have just m dependent variables. So if variational derivative of L vanishes on epsilon, on the infinite prolongation, then we have the formula 6. In fact, Lagrangian L determines a unique element of the quotient space 7. As you can remember, omega L in the formula 6 can be chosen in a non-unique way. there is some arbitrariness in the choice of omega L, but still each Lagrangian L determines a unique element of the quotient space 7. That's why we have to consider a quotient space, actually. And further, I must say that further we deal with Lagrangians such that the corresponding Euler Lagrange equations are at least differential consequences of the original system. In some sense, they can be degenerate then. So they can produce, such Lagrangians can produce just consequences of the original system. And some of them can produce the original system itself. We do not distinguish between them, actually, because we deal with Lagrangians from the intrinsic point of view, and it's not so easy to distinguish between from the intrinsic point of view.
Sorry, what do you
yes.
What do you mean by at least differential consequences? And
no,
something
at
more?
At least it means that we consider both Lagrangians that produce the original system itself and the Lagrangians that produce just differential consequences of the original system, but not the original system, for example.
Okay.
So we deal with both of them, with both of these situations, both of these kinds of Lagrangians. So each horizontal form determines the corresponding horizontal cohomology element. We just can consider horizontal form modular image of the horizontal differential. And since composition of the Euler operator and horizontal differential equals to 0, we can consider Lagrangians as horizontal cohomology elements, not just as horizontal cohomology forms. In this case, we can generalize the previous result as follows. So if horizontal cohomology element of L is an element such that E of L vanishes on the epsilon, then there is the corresponding element of the quotient space 8. This quotient space is the central object of my topic, of this topic. So an internal Lagrangian of an infinitely prolonged system of equations, epsilon is an element of 8 of this quotient space, actually. I don't know why my numeration changed. Okay, so internal Lagrangian is just an element of this quotient space 8. Can you see my mouse? Or not?
Yes.
Oh, okay. Very good, thank you. So once again, internal Lagrangians are just elements of the quotient space 8. As far as I can see, as far as I know at least, they encode Lagrangian formalism in intrinsic geometry terms, intrinsic geometry terminology. Internal Lagrangians allow one to reconstruct action principles. However, in the general case, the corresponding actions are defined ambiguously. If L produces an internal Lagrangian of epsilon, then it admits an extension to jets such that the formula 9 holds. Here, by extension, I mean some differential formula on jets, a differential form on jets, such that its restriction to epsilon coincides with L. So we have for each representative of an internal Lagrangian, we have such an extension. And the extension that is written under the formula 9. This extension is quite special. Of course, here I is the ideal of epsilon in the algebra of smooth functions. It means that this ideal consists of functions that vanish on the system epsilon. So here we have decomposition of the form at least twice Cartan form plus some differential form with components that vanish on the epsilon, on the system epsilon. And that's why this decomposition, that's why this extension is quite special. Of course, we need for such extension that its exterior derivative can be written in the form 9. So it should be written in the form of the sum of twice Cartan form, at least twice vertical form, and some form which with vanishing components, with components that vanish on the system epsilon. So, and here we obtain the following theorem. I decided to omit the proof of this theorem, to be honest. It's not so difficult, and it can be found in the paper, in my paper on archive. So the theorem: let L be a differential on form such that dL is at least twice Cartan form on this system epsilon. It means that L represents an internal Lagrangian. Suppose that L, capital L with tilde, is its extension of the form 8. Then we have two facts. First of all, the variational derivative E of horizontal representative of L tilde vanishes on epsilon. It means that we reconstructed from L, we reconstructed L capital with tilde, and it's just a Lagrangian that admissible for our system. Its variational derivative vanishes on epsilon. And also L and the horizontal class of L tilde, of L capital tilde, produce the same internal Lagrangians. That's why we can say that we just...
Bad notation, because just above I denotes the ideal of E, and so this is completely different.
Yes, it should be L and it should be I, but somehow they became the same letter. I mean that literally they are different letters, but there is no difference between them here. Yes, bad notation, sorry, it's my fault. The ideal of epsilon arise only here. All of other letters that looks like I are just L. And L denotes a representative of some internal Lagrangian. So we can reconstruct action principles, but this reconstruction is not uniquely defined. We can reconstruct variational principles in several ways. But systems of equations in an extended Kovalevsky form admit a canonical way to restore an action from an internal Lagrangian. Speaking about systems of equations in evolutionary form, evolutionary systems of equations, they also admit a canonical way to restore an action from an internal Lagrangian. Of course, they are just systems of equations in an extended Kovalevsky form too. But they have the corresponding way to restore an action from an internal Lagrangian is quite special for them. Of course, it allows one to restore the original Lagrangian. If we have some Lagrangian for the system, and this Lagrangian produce the internal Lagrangian, then we can restore the original Lagrangian from the internal Lagrangian itself. So, and now I'm going to discuss spectral sequence for Lagrangian formalism. So it's just second part of my talk. Let us recall that internal Lagrangians are elements of the quotient space 10. This group is canonically isomorphic to the n-1 cohomology of the complex 11. Here I just changed numeration. The numeration is quite special here. I will explain this decision later, why I decided to change numeration. But as you will see, I decided to change the numeration for sake of simplicity. Of course, I'd like to merge two spectral sequences later. So the differentials D are just induced by the Ram differential or by the exterior derivative. So yes, and So we deal with cohomology of the factor complex here. Then it makes sense to consider the filtration. Just lambda means just usual the RAM complex, then twice Cartan complex, at least twice vertical forms, thrice Cartan complex, and so on. This filtration allows us to obtain the corresponding spectral sequence. I denote this spectral sequence with tildes. So this filtration produces the corresponding spectral sequence.
So this is just Vinogradov's filtration, but the first term is missing. Yes.
Yes, it is. Yes, I will speak about it later. Yes, it's just Vinogradov's filtration, but there is no first term, no just Cartan forms. Filtration begins with twice Cartan forms here because of complex 11, because of the definition of internal Lagrangians. So we have nothing to do with it, just definition, and we have to omit the first term in this filtration. Further, we assume that the drum cohomology groups of epsilon are trivial in positive degrees. Then we can make some remark, namely the group of internal Lagrangians is isomorphic to the n plus first cohomology of the complex of twice Cartan differential forms, because it follows immediately from the fact that here we have a factor complex, and if cohomology of this complex are trivial in positive degrees, then cohomology of factor complex are directly related to cohomology of twice Cartan complex, and that's all. That's why group of internal Lagrangians is isomorphic to the n plus 1 cohomology of the complex C2 twice Cartan forms. This cohomology group admits no other description in terms of variational B-complex. Here I must say some words about this phrase, I guess. Variational B-complex is another way to describe Vinogradov's spectral sequence. Both descriptions are canonically isomorphic. Vinogradov's description and the description using variational B-complex. They are canonically isomorphic, but they are not literally the same. The difference is that you have to deal with equivalence classes in Vinogradov's construction, and variational B-complex just deals with horizontal representatives of the corresponding equivalence classes. So these two constructions are canonically isomorphic, of course, but they are not literally the same. In the situation under discussion, there is no another, at least even canonically isomorphic description of this cohomology group, of cohomologies of this twice Cartan complex. So if you prefer to deal with variational B-complex, for example, then you have to rewrite these groups in the terminology of variational B-complex literally. There is no another description. The reason I decided to discuss it here is, I decided to discuss it here just because I get that if you want to deal with presymplectic structures in some special way, if you want to define presymplectic structures as derivatives of internal Lagrangians, then you may regard n plus 1's cohomology of this complex as presymplectic structures. However, in this report, I will not use this definition of presymplectic structures. I will use another one definition, and I will tell about it later.
I'm sorry again. What do you mean by variational bicomplex? I think that not. You mean the bicomplex that arises due to the structure of the bundle.
Of bundle. Yes, there is two.
But how can this construction be canonically isomorphic to Vinogradov's one? Since Vinogradov's construction is invariant, and
yes.
Well, it is broken when you change coordinates.
It's true. So I have to make some explanation here. Yes, that's right. These two constructions are canonical isomorphic in the case when you consider your equation as a bundle. Of course, Vinogradov's construction is much more invariant. Of course, in Vinogradov's construction, you need not to consider equation as a bundle. You may consider equation just as an infinitely dimensional manifold, or just manifold with the Cartan distribution. You need not to remember about the base. But if you prefer to remember about the base space, then these two constructions become canonical isomorphic, then variation will be complex arise. It makes sense. It becomes to make sense in this case, and they just canonical isomorphic in this case. But of course, yes, Vinogradov's construction is much more invariant in the sense that if you, for example,
if the bundle structure is fixed.
Yes, they are canonical isomorphic for
yes,
each bundle structure. Yes, for bundle structure. For example, if you want to make some transformations like Khodogrov transformation and so on, variation will be complex, makes no sense in this situation. Just Vinogradov's spectral sequence remains invariant in this sense. Yes, and let us recall that the filtration of the RAM complex by all the powers of the Cartan forms, of Cartan complexes, produces Vinogradov's spectral sequence, C spectral sequence. So the difference between the filtration of the previous page and the Vinogradov filtration is just this one term, this term of Cartan forms. So then we can say that the spectral sequence with tildes of the previous filtration is related to the Vinogradov C spectral sequence. And namely, the relation between these spectral sequences is based on the identities which are presented here. It is presented here. And besides, the terms of the corresponding complex arise in this tilde, in this spectral sequence with tildes. Complex 10 is just complex 11, actually, of the complex 11. Terms of this complex are just zero terms of zero page of the spectral sequence with tilde. So we obtain the differential d tilde, which actually sends internal Lagrangians to presymplectic structures. So it's time to define presymplectic structures here. By presymplectic structures, I mean I will mean just elements of this group, E2 and -1 at the first page of the Vinogradov C-spectral sequence. They are presymplectic structures, and then this differential D1 with tilde sends internal Lagrangians to presymplectic structures. So here we have an analogy between internal. Oh, yes.
I'm sorry. You mean any term, any element of this term of E2 and n-1, it should be closed.
Yes, it should be closed, but they will be closed actually, just because of this construction, they will be closed. Of course, they will exactly in this sense.
Images of E tilde.
Yes. Oh, yes, okay. Yes. That's right. Yes.
Sorry.
Yes, variationally closed two forms. So this model can be considered, not model, this group can be considered, or linear space can be considered as a space of variational two forms. Here, index 2 means that it's just two forms. And by symplectic structure, I mean a closed two form, closed in variational sense, in the sense of the corresponding complex. And here we have an analogy between internal Lagrangians and conservation laws, namely the differential D1 with the same structure of indexes, but without tilde. It's a Vinogradov's differential. Since conservation laws, that is variational 0 forms, to variational 1 forms. And let us recall that casymmetries or characteristics of conservation laws, if you want, allow one to describe only variational one forms. In fact, they give us description of variational one forms, but not variational zero forms itself. So they describe not conservation laws, but their derivatives in the Vinogradov sense. And if kernel of the corresponding operator D1 is non-trivial, then we have some non-trivial conservation law which cannot be described by casymmetries. Of course, this conservation law cannot be described by variational one forms. And casymmetries are just describe variational one forms. To be honest, I don't know any examples of such conservation laws. And more than that, I saw the paper by Peter Olver. He wrote it in 1986, where he discussed this question. And several weeks ago, I asked Peter Olver about this problem, if he knows any new results in this direction. And he answered that he knows nothing new, actually. He knows, he doesn't know any examples of non-trivial conservation laws with trivial characteristics, with trivial casymmetries still. But still this situation, this description of conservation laws motivates us to give the following definition. A hidden Lagrangian of an infinitely prolonged system of differential equations is an element of the corresponding kernel of this differential. So hidden Lagrangian is a Lagrangian such that the corresponding derivative is trivial. This Lagrangian produces trivial presymplectic structure, in fact. That's why such Lagrangians are hidden. Of course, they are hidden for presymplectic structures. There is no presymplectic structure. Here, presymplectic structures play a role of casymmetries, in fact, but they play this role for internal Lagrangians, play a role of casymmetries for internal Lagrangians, and the similar problem arises if there are any Lagrangians such that, if they exist, any Lagrangian, such that its derivative T1 with tilde is zero, such that the corresponding presymplectic structure is just trivial.
Of course, but these hidden Lagrangians may exist only for equations with more than two lines in
Yes, I will discuss it later. Yes. Such hidden Lagrangians may exist only for non-L normal equations. I will discuss it later, actually. And another definition of an extendable presymplectic structure. I will say that the presymplectic structure of epsilon is extendable if it is generated by some internal Lagrangian, if it belongs to the image of the previous differential D1 with tilde. And the first page of the spectral sequence with tilde, of the spectral sequence for weird filtration, reads as it's written here. So the first page we can see it here, and let's assume that we deal with a hidden Lagrangian, then it belongs to the kernel of this differential, so it stays alive here. And then this hidden Lagrangian, the differential on the second page just sends this hidden Lagrangian to this term, but on the second page, to the term 3n minus 2, but on the second page of the Vinogradov's spectral sequence. The term 3n minus 2 still belongs to the Vinogradov spectral sequence. Of course, here we have just Vinogradov's groups on the first page. Later, this group, for example, this group 2n minus 1 will be changed on the second page. It will not be Vinogradov's group. Of course, to calculate E2n minus 1 on the second page, we have to deal with kernel of this differential, Vinogradov's differential. modulo the image of another differential, not Vinogradov's differential. So this group on the second page, E2 and -1, is not Vinogradov's group already, but this group is still Vinogradov's. Of course, here we have to deal with the kernel of this differential, modulo the image of this differential, which is also Vinogradov's still. So at least on the second page of this spectral sequence with tilde, we have a mapping from hidden Lagrangians to this group E3, 3, and -2 on the second page with lower index 2. And the relation between these two spectral sequences implies the following theorem. I decided to omit details of the proof also, but theorem as follows. First of all, the description of internal Lagrangians of ODEs completely reduces to presymplectic structures, as well as the description of internal Lagrangians of L-normal differential equations. Here, I must recall that L-normal differential equations are just differential equations that admit no gauge cosymmetries in some sense. They, okay, let's say that they admit just no gauge cosymmetries. The phrase that
what do you mean by gauge cosymmetry? What do you mean by gauge cosymmetry? I don't understand.
Yes, it's not so easy. I forgot to write
no
it
one knows
here. Yes, maybe it's true. So, for example, at least if we discuss Euler Lagrange equations, then L-normal equations are just equations without any gauge symmetries. If we discuss Euler Lagrange equation, then cosymmetries become symmetries, and non-existence of gauge cosymmetries is just non-existence of gauge symmetries. So this system, a normal Euler Lagrange system of equations, is just a system of equations that has no gauge symmetries, gauge symmetry group. Besides, we obtain the following result. If an infinitely prolonged system of equations admits a compatibility complex of length 3, then the group of its hidden Lagrangians is isomorphic to the group 3 and -2, 2 of the Vinogradov C-spectral sequence. The reasons of this point 2 were discussed above. The reasons for this result were discussed above. Explanation of this result. And the third conclusion is that conic systems of differential equations admit neither hidden Lagrangians nor non-extendable presymplectic structures. By conic systems of differential equations, I mean systems of equations which admit rescale of dependent variables only. Conic, a system of differential equations is conic if it admits symmetry, a rescale of dependent variables only. Such systems of equations have trivial second page of the Vinogradov C-spectral sequence, and that's why the description of variational principles for such systems just reduces to presymplectic structures as well. Well, and also we can conclude that the group of hidden Lagrangians of system of equations with two independent variables is isomorphic to this group again. The group of hidden Lagrangians of an irreducible Lagrangian gauge theory is isomorphic to this group again. By irreducible Lagrangian gauge theory, I mean a gauge theory that is irreducible on shell. There is no reducibility on shell here, on the equation manifold itself. And besides, we can conclude that the vacuum-Einstein equation with their cosmological constant and abelian performed theories do not admit hidden Lagrangians or non-extendable presymplectic structures, or they are conic. In fact, I'd like to recall that the vacuum-Einstein equation is the equation Ricci tensor equals to 0. Ricci tensor of a metric is equal to 0. This equation is conic, of course, if we rescale a metric, the metric G, then Ricci tensor remains unrescaled. So the left-hand side of this equation remains unrescaled, and rescale of G is a symmetry of this equation. That's why this equation is conic. And the similar situation holds for abelian performed theories. However, here we can rescale A is just a perform on some manifold. If we rescale A, then we rescale the left-hand side of this equation. It means that the rescale of A is also a symmetry of this equation, or system of equations, if you want. It means that these equations do not admit hidden Lagrangians or non-extendable presymplectic structures. However, if you consider the vacuum Einstein equation with non-zero cosmological constant, the situation may be different, and I guess that I have no rigorous proof, but I guess that such an equation admits no symmetries but K symmetries, and it means that this equation admits no variation of one forms, and then its presymplectic structure lives on the second page. Its presymplectic structure stays alive until the second page of the Vinogradov spectral sequence. So I believe that the vacuum Einstein equation with non-zero cosmological constant has non-trivial second page of the Vinogradov spectral sequence. So speaking about the second question of my talk, I guess that the concept of presymplectic structures is not complete in this sense. It's just not enough to consider presymplectic structures, and we need something else like these internal Lagrangians. Of course, I guess that there exist some system of equations like irreducible Lagrangian gauge theories, gauge systems of equations with non-trivial group E3 and -2, 2. But I have no any examples of such systems of equations. And now I'm going to discuss the results. So let's consider some speculation at first. Let epsilon be an infinitely prolonged system of Euler Lagrange equations of a certain Lagrangian L. Assume that epsilon also possesses a hidden Lagrangian. Then we get several internal Lagrangians determining the same symplectic structure, not presymplectic, but symplectic. Of course, this symplectic structure arises from Lagrangian that produces the system of equations under consideration. Thus, the symplectic structure doesn't allow one to distinguish the internal Lagrangian generated by the horizontal form L from some other internal Lagrangian. So, in this case, the concept of presymplectic structures is just not enough. And another speculation about on this topic, for example, is if you will find an example of a system of equations with a hidden Lagrangian, and this system of equations will consist of m equations for m unknown functions, for m dependent variables, then you can consider its cotangent bundle, which in fact has the same second page of the spectral sequence. So if you will find such an example of a system with a hidden Lagrangian, then its cotangent bundle will be example of this situation. Cotangent bundle will possess a hidden Lagrangian, and it will possess a certain Lagrangian L that produces this cotangent bundle. So we just need to find some example of infinite prolonged system of equations with a hidden Lagrangian here, such that number of its equations equal to the number of its dependent variables, its unknown functions. So it would be interesting to find an example of such a system among physically significant equations. However, even for conservation laws, a similar problem is not trivial, is apparently hasn't yet been solved. Similar problem, by similar problem, I mean a problem of constructing a non-trivial conservation law with trivial cosymmetry, with trivial characteristic. Nevertheless, for theoretical description of variational principles for theoretical description of variational principles in intrinsic terminology. It seems more preferable to use the concept of internal Lagrangians rather than the concept of presymplectic structures. The question of whether there are hidden Lagrangians or non-extendable presymplectic structures deserves special attention, at least to my mind. So, and that's just all. Some literature here. And thank you very much for your attention.
Thank you, Kostya. Very, very interesting questions, remarks. Well, I always was sure that existence of a presymplectic structure is sufficient for equation to be a Lagrangian one, but I see that I was wrong.
Well, yes, I have no examples of the situations.
Well, of course, to construct an explicit example is not easy, but I'm sure they exist.
Yes, I'm sure too.
Questions, remarks? No. Okay, then thank you very much again for your talk. Very instructive and very interesting. Thank you for attending our seminar. Thank you to everyone. And we make a break till the end of April because I go on holidays. Goodbye and see you on, I believe, 24th of April. Goodbye.
Okay. Thank you. Thank you once again. Goodbye.